This problem is a little more challenging of a flux problem. In this case, we have some wire with a current flowing through it, creating a magnetic field, and then you've got some loop in the field, and you want to find what the flux through this loop is. The first thing that comes to mind, well, that's just going to be an easy problem, right? That's just going to be B dot A, or maybe even just magnitude dA. Well, it's not that simple, and the reason it would be this if the magnetic field were uniform here, but it's not uniform here. And why is it not uniform? Because it drops off. It's created by the wire, and we know a wire creates a magnetic field that drops off with 1 over r squared. So the magnitude of the magnetic field from a wire is equal to mu naught I over 2 pi r. But the problem is, as you move farther away from the wire, I'm sorry, did I say 1 over r squared? I meant 1 over r. Biot-Savart's law has 1 over r squared, but once you integrate, you get this expression. Okay, so as you increase r, as you move farther away from the wire, the field gets weaker and weaker. So the small portion of flux is going to change, if you want to think about it that way. So the amount of field passing through this part of the loop is not the same as the amount of field passing through a little part over here. So that's where we have to go back to the definition of flux. So the flux is B dot dA, and of course remember I'm not putting the little loop on this integration sign because this is not a closed surface. This is just one little loop. Okay. So usually with these problems we then pull B outside of the integral and we proceed, but like I said, we can't do that because B depends on the position R. So what we're going to have to do is we're going to have to take some little slice of this loop. It's going to have some area. We'll call this dA, and it's a distance r away from the wire. So we can then proceed to say, well, we know the cross product, or the dot product, excuse me, is equal to B dA cosine of phi. I'm getting rid of the vector bars there because this cosine takes away the vector bars. But what is phi? Phi is the angle between the differential area element and the magnetic field. Well, the magnetic field is, if you use the right-hand rule, point your thumb in the direction of the current, your fingers point in the direction of the magnetic field, so the field is into the board everywhere. Everywhere on this side of the wire, that is, which is all we care about. Of course, its magnitude changes with r, but we know the direction. And since that is downward and which direction is the area element? Well, the area element is going to be perpendicular to the surface, so that's going to be downward as well. You could say it's upward, and then you're going to have a negative sign. It doesn't matter here, but it's just one loop. So let's say it's downward, just so it's the same direction. So phi equals 0 degrees, and this drops out. This comes to 1. So this is just equal to B dA, the integral of B dA. Like I said, we can't pull B outside the integral because B depends on R. Also, the area, what is A? dA. Well, the area of this little sliver is going to be B, that is fixed, times whatever dr is, dr. So this equals B dr. So this change in R times B. So I can plug these two things in. So at the integral of mu naught I over 2 pi r, which is this, just plugging that in for B. I can also plug that in for dA. So b times dr. So this is actually a fairly easy integral. I can pull out all the constants. Mu naught I is constant, 2 and pi a constant. Oh, and b is there as well. Pull all that out, and what I'm left with is the integral of 1 over r dr, and that is evaluated from c, this is a distance c away from the wire, to c plus a. Okay, and we know that the integral of 1 over r is just natural log of r. So this is going to be natural log of r, and that is evaluated from c to c plus a. So we can evaluate this at its limits. Mu naught I b over 2 pi times natural log of c plus a minus natural log of c. Now we are essentially done with the problem, but we're going to simplify things a little bit, make it a little cleaner. So when you subtract two natural logs, you can write that as natural log of c plus a over natural log over c. And then I can divide c into each one of these. C divided by c is 1, a divided by c is, well, you can't simplify that. So this equals mu naught IB over 2 pi times the natural log of 1 plus a over c. Why did I reverse the order? I don't know. I like the 1 in the front. So that is the answer.